Okay, welcome to lecture here. We're going to get started here in just a second. Sorry about that. Just a little slow loading today. Um, we're going to pick up where we left off last time in lecturing. So we're still in chapter 17, towards the middle and end. And we'll continue on at that point. So we should have left off, I think, in the notes somewhere around here. Again, on your notes, you may have a slightly different table, but it's a similar one that you find in your book. Okay, so as usual, if you have any questions, please feel free to ask them in the chat box as we go through. Again, even if we sort of pass where we're at, we'll come back to it. So we've been talking in this chapter about electrochemistry. It doesn't look like you guys get to see the screen, huh? Let me take on a sec. Technology. Let's give it the old try here. Let's try that one there. That hopefully should be better. I think you can see the screen, I hope, at this point. There. Okay. So we've been talking about electrochemistry in this chapter. We started off talking, again, sort of a review of redox reactions. Remember, redox reactions are oxidation reduction reactions. So oxidation, for the most part, what we deal with here in general chemistry is the loss of electrons, while reduction is the gaining of electrons. And we can balance those equations sort of simply by just adding electrons to each of the half reactions. Remember that when you do balance the equations, you always want to make sure that the electrons are equal to each other in both half reactions, so they should completely cancel out. And the idea behind that obviously is as one loses a certain number of electrons, the other substance will gain same amount of electrons. So they should always be balanced. We also talked about balancing a little bit more complicated redox reactions in both acidic and basic solution. And again, that involves the adding of water, the adding of H plus, and also the adding of OH minus if it's a basic solution. So we went through all that. Then we started picking up sort of really where the chapter truly sort of begins with galvanic cells. And galvanic cells are really just a redox reaction that's occurring. And a galvanic cell basically has several parts to it. It has one part which is known as the anode side of the cell. And in a traditional galvanic cell, we can build in the laboratory, for example. We can take some beakers, we'll have some solutions in each of those beakers, and then we'll have some solid electrodes. Now, the solutions in the beakers typically will match the electrode in terms of the element. So for example, if you had a solid copper electrode in the solution, you probably have some type of solution that had copper 2 ions, for example, flowing around. If you had a zinc electrode that was solid in the solution, you would have something that has perhaps zinc ions floating around in it. And the anode side is where oxidation occurs, so electrons are lost from that side. Travels across the wire, and as those electrons are traveling, they could do some type of work, and we typically look at it in terms of voltage, and it could go to the other side of the cell, and on the other side of the cell, that is where we have our cathode side, and on the cathode side, that's where reduction occurs. So those electrons that travel from the anode side to the cathode side participate basically in a reduction. So for example, if you had those zinc ions floating around on the cathode side, those electrons would come in and the zinc ions would gain those electrons and obviously go from being in the solution to sort of being solid is typically what happens, sort of plates out. Now, usually the two sides, the cathode and the anode, are connected by a salt bridge. Salt bridge typically will have some type of ionic compound in it. And again, that's a positive negative guy, obviously, if it's ionic. And that helps, again, as we talked about, sort of keep the charge level on each side to allow this sort of electrons to travel from one side to the next. You know, there's sort of a potential difference, which is sometimes referred to between, say, the cathode side and the anode side. And that sort of difference, that positive difference, helps bring those electrons across the wire. Now, again, if you didn't have that salt bridge, at some point you would build up some negative charge and positive charge on each side of those beakers, if you will, and that will eventually make the cell obviously not work as right as it should or function as properly as it should. And again, that sort of salt bridge, which is typically in there, helps really mediate that buildup overall of charge on each side and keeps it really sort of functioning well for a long period of time. We talked about that you could calculate the cell voltage, which is also sometimes referred to as the cell EMF, or the cell potential, but it's really all just calculating the voltage. And there's really an equation that we solve to do that, and that is basically our E of the cell is E of the cathode minus E of the anode. And we look those values up in an SRP table. Remember, the SRP table is a standard reduction potential table. And that means that they are all written as reduction reactions, as we saw in that table. And the E value for those in those tables are specific for how they're written, which means, technically speaking, in all sort of galvanic cells, you should have a anode side or an oxidation that's occurring, which means, technically speaking, you should have to reverse those reactions that you find in that table. And as we talked about, if you reverse the reactions in the table, you technically should also reverse the sign that you find in that table. So for example, if you had 2E plus A goes to A2 minus E naught equals minus 0.5 volts. This would be our reduction, right? Again, gaining electrons. If we flipped it around for our oxidation, technically speaking, we should have A2 minus goes to 2 electrons plus A. And in terms of the E value that would be associated with that, we would change the sign. So the E naught for this guy would end up being positive 0.5 volts. And that brings up a lot of confusion sometimes when people go to use this equation. Again, as we talked about last time, there's really sort of two thought processes when people use this equation. They can use this equation and you can basically take the values from the table, and even though technically speaking one of them should be reversed and the E value should be changed in terms of the sign, you would not change it if you decide to use this equation and subtract. And the reason you wouldn't do that is really, that's why it is a subtraction here. That subtraction will change the sign on the anode one for you. So we talked about, if you decide you want to use this one where you subtract, you should just take the values from the table and basically just put them in exactly the way they are. If you want to sort of correctly sort of write everything, obviously with sort of the correct E value like you would find here, you actually should add them together. So again, if you decide you want to just kind of change everything, you want to make sure everything has the correct sign with the correct half reactions, which is perfectly the right way to do it as well. You do want to add here if you change the sign. So the simple rule is, if you take it from the table and you don't change the sign, subtract. If you take it from the table and decide to change the sign yourself, you should add. And again, they both, again, should get you the same answer as long as you don't do both of those things sort of together. So you don't like change the sign and then subtract, because you'll undo it. Now, when we have no information about how the reaction is occurring, we could simply use the SRP values to determine what will be our anode and what will be our cathode. And in that particular case, the one that is more positive value on that table will be our cathode. Now, there is sort of a rule with that, which is that if the problem does sort of tell you what's going on, so they tell you exactly how the reaction is occurring, they give you an overall reaction, then you do have to look at that reaction to determine what's your anode and cathode. You have to look at the reaction to decide what's being oxidized, which then would be your anode, and what is being reduced, which would be your cathode. So the more positive thing, which people also sometimes get in trouble with, is, again, specifically for situations where you're not given any information about how the reaction is actually occurring. You're just said, hey, you built the cell with these two things. But again, if they give you a reaction, you do need to basically look it over and see what's happening. Now, we then sort of tied together, I'll come back to this page we scribbled on last time. We did tie together basically some of our thermodynamic properties and our reaction and our electrochemistry type stuff that we talked about. So a couple of things just to kind of review this one as well, kind of where we left off. We can use our delta G along with our E of the cell. So the delta G, which is our Gibbs free energy, would equal minus NFE of the cell. N is the number of electrons, so that's the total number of electrons that have been transferred from the anode to the cathode. F is Faraday's constant, which is 96,500, again, a constant. And E of the cell is our cathode minus our anode. And again, you see two versions of this, one without the knot, one with the knot. Again, the knot means basically standard conditions. And for the most part, that's probably what you'll use in each of the, and most of the calculations that you sort of do. Now, the reason we sort of can use this, and this helps us understand whether or not a reaction will sort of occur spontaneous or not, is if we end up with a positive value for our cell voltage, which is our E of the cell, that will give us a negative delta G. So as we talked about with delta G, negative value means that the reaction would be spontaneous. So really, as soon as you kind of see E of the cell as a positive value for the voltage, you kind of already know that this reaction is going to be spontaneous. And what that means is it should proceed from reactants to products. And we could also tie our E of the cell to our equilibrium constant. And there's three sort of equations on this page that we talked about, but really the one in the box here is the one that you could use. E of the cell, which again is our cathode minus our anode, is equal to RT over NF, natural log of K. R is our gas constant and is the one with energy, which is the 8.314 version of it. T is our temperature in Kelvin. N is our moles, again, of electrons, and F is Faraday's constant. And K obviously is our equilibrium constant, products over reactants. Now, the two bottom equations are sort of shorthand versions of this equation here in the box, and it's shorthand versions for when you're at 25 degrees Celsius. At 25 degrees Celsius, all these guys up here, the 8.314, the 298, the 96.5, 100 is basically all sort of a constant value, and you get those two versions on the bottom. Again, like I said, it's probably easier just to remember the guy in the box and just plug and chug in there all your numbers, even at 25 degrees Celsius. I will say that if you use one of these three sort of versions of this equation here, you may get a slightly different answer in terms of your final answer, not really in terms of perhaps the exponent part, for example, something like if you're calculating K, but the front part of the number may be slightly different depending on sort of which one you choose and the rounding that you do, because as we'll see in maybe some examples here, if you're going to calculate something like K, at some point you'll do like the E, or the inverse of the natural log, and depending on how you round that, you might get a slightly different value. And on the right-hand side of the screen here, again, is our relationship between our thermodynamics, our equilibrium constant, and our electrochemistry, and really sort of the three equations that tie them all together. Again, our delta G equals minus NFE, our E of our cell getting to our equilibrium constant, and our delta G that we saw in the previous chapter. All right. Any questions on any of that stuff that we covered last time, I think? Okay, so again, remember, if you do have questions, feel free to ask them. And here's a table, not the exact one that's in your book, but I believe you have a similar sort of table in your book. And basically, we could look at this and our delta G with our equilibrium constant and all those sort of equations kind of put together. And what we see is really the same relationship when we know about our equilibrium constant. So obviously, if we have a large value of K, that would mean that we should expect products at equilibrium, which would imply that the reaction is heading from reactants to products, which should also imply that the E of the cell should be positive, which means it would be a spontaneous reaction, and would also imply that the delta G should be negative, which would also imply a spontaneous reaction. Opposite is true if we have a equilibrium constant that really is less than 1 or a small value. Just like we already know about the equilibrium constant, we would assume that that would be a Motingly reactants at equilibrium, and that usually will result in a E of the cell that's negative, which means it's non-spontaneous. Again, that E of the cell that's negative will affect here. Again, if this is negative and it has the negative in here, these two negative guys are going to turn our delta G into a positive number. And we know that positive delta G means it's a non-spontaneous reaction. And again, if you're at equilibrium constant equals 1, the natural log of 1 is 0, and that's going to basically zero out our delta G value and our E value. And again, you're sort of on the fence at that point. You're kind of equally favored both reactants and products. All right, so now we did all that review. Let's do some calculations here. Calculate the delta G for the following reaction and determine whether or not it is spontaneous. So you do have the half reactions there, the SRP guys, and their values. So take a minute or so and see what you come up with, and then we will talk about it. Okay, so let's take a look here, but let me answer your question first. So the equations with the those two numbers there are basically the equation that basically involves the equilibrium constant. So it would definitely be an equation where it has something to do with the equilibrium constant. And again, those two versions of that equation are sort of just a shortcut versions of those equations that occur at 25 degrees Celsius, which you usually can assume in most cases. But it would involve the equilibrium constant one. So it's really it's those two equations is really this equation. And again, as you can see, you would want to use this equation when it involves the equilibrium constant or E of the cell, something to do with the equilibrium constant. And again, these two guys here are just sort of reduced versions of it. You actually can use either one. If you want to use, it's just the difference is just one's the natural log and one's the log of base 10. Technically speaking, they all should give you the same answer. If you choose this equation, or this equation, if you're at 25 degrees Celsius, they all technically should give you the same answer. I will say though, in sort of practice, that's what I was talking about earlier. Sort of in practice though, if you're doing a problem and depending on which one that you sort of choose, and depending on how you round, you may get some slightly different answers, again, because you're involving logs and inverse logs and those type of things. So technically speaking, they all should give you the same answer. And sort of real life application, you know, you may get a slightly different answer depending on which one you choose and sort of how you round as you're doing the problem. But again, like I mentioned before, sometimes people really just sort of ignore the bottom two guys and just go with this, because even at 25 degrees Celsius, you can just go with the one in the box and just plug in the numbers, and everything will come out the same. Okay. So let's take a look at this one here. We're looking for the delta G of this reaction. And again, we pretty much have just the SRP values given to us, so we can use the delta G equals minus NFE. And we do want to figure out E of our cell. Again, E of our cell is going to be our E of our cathode minus E of our anode. So we do want to figure those out, obviously, here. And in this particular reaction, the cathode is going to be our copper 2, while our anode will be our iron 2. And in this case, it is because when we look at the copper 2, it's going from +2 to 0, basically heading in that direction. And that means it's going through reduction. While if we look at our iron, it's going from 0 to +2, going in that direction, which means the iron is going through oxidation. So here again, that's how we can determine our cathode and our anode, which means our E of the cell, if we put it in there, I again am going to be subtracting here. So I'm not going to change any signs. That means I'm going to take 0.34 volts minus a minus 0.44 volts. And I'm going to grab a calculator and see how we do. That looks like 0.78 volts. Would be my E of this cell. Not really what it's asking for here. It is asking for our delta G. But we do need to find our N. And our N in this case is going to equal 2. And as we talked about last time, you don't add both of those numbers together. Again, N is the total number of electrons that are lost by the anode and then picked up by the cathode. And in this case, is basically 2 being transferred. And that's pretty much all we need for our delta G at this point. Our delta G will equal minus N, which is 2. Our F, which is our Faraday's constant, 96,500 joules per volt per mole. And our E of the cell, which we calculated up there. Again, our volts will cancel, our moles will cancel. Here we will be left with joules, and it looks like we will be left with something like negative 150,540 joules, are about 151 kilojoules, give or take, depending on rounding. Any questions on that calculation? We know that this reaction should be spontaneous for a couple of things. We know that, truthfully, we knew it was a spontaneous reaction right about here because we got a positive E of the cell. And as we can see as well, we got a negative delta G. And both of those things means it is definitely spontaneous under these conditions. Any questions on any part of that calculation there? Okay. So why don't you do this one? The question is, will 1 molar nitric acid dissolve gold to form 1 molar gold-3 solution? Again, here are our SRP values from the table. So take a couple of minutes and calculate whether or not this basically will happen. So is this reaction going to be spontaneous or non-spontaneous based on what it says? And we'll talk about it in a second. Okay, so in this particular case, we want to know will this basically occur? So it means there's really a couple of ways you could kind of calculate it or figure it out. Probably the easiest way would be just to calculate E of the cell. And again, that's going to be our cathode minus our anode. And here again, if we end up with an E of the cell that's positive, we know it's going to be spontaneous and it will occur. Again, if we end up with a negative, it's going to be non-spontaneous. And obviously it would not occur. So to help us decide that, obviously we need to determine our cathode and our anode. So in this case, you may look at this and go, oh, this is more positive. So that's going to be our cathode. And this will be our anode. And if you sort of did that, you would be wrong in this case. So that would be the wrong choice. So again, a reminder that although you can use the SRP values and the one that's more positive will typically be your cathode, you do have to look at the problem or the reaction and see what's essentially happening. So if you just read what it says, it wants to know if you take nitric acid, will it dissolve gold metal, which is gold with no charge, to form gold with a charge. So if we look at the arrangement here, it is actually the bottom reaction that needs to be reversed in order to give us the correct way that the reaction is occurring, which means in this case, this guy is actually going to be our anode. And actually in this particular case, this is nitric acid right here. That is going to be our cathode. So again, this is a very good reminder that you just can't just kind of without thinking go, okay, so this one's more positive or not. You do have to look at equations that they give you, the reactions. You do have to look at what they're saying, the reactions happening, and make sure that you sort of choose the right one. So now that we got this sort of correct setup here, we could take E of the cell is our cathode, which would be 0.96 volts, minus our anode, which would be 1.5 volts. And that's going to get us minus 0.54 volts. And really at this point, that's probably all you need, because we know that this is a negative cell voltage, which means this reaction is going to be non-spontaneous. Again, you could confirm it if you wanted to go to delta G. Again, be minus 3 for our electrons here, it looks like, our 96,500, and then obviously our negative 0.54. Not really worried about the number, but again, our negative and our negative here gonna turn our delta G into a positive. So we got, again, a positive delta G, which means non-spontaneous. We have a negative cell voltage, which also means non-spontaneous, and this will not occur. And that's how they used to test gold, like in pawn shops and stuff, right? They put a little bit of nitric acid on it. If your jewelry's still there, it's probably gold. If it kind of goes away, it's not so much gold and that type of stuff. So any questions on this particular one here? So obviously this reaction would not occur. The nitric acid would not dissolve the gold metal in this particular case. Any questions on that? Yeah, so I think your question is, why in this case did we perhaps not go with the more positive one? And really the reason we didn't go with the more positive one, which typically would be your cathode in this particular case, is because specifically in this question, they were asking for this reaction to occur basically on the reactant side on this, right? Now, if we flip the top one, which is typically what you would do if that's the anode, because the anode is technically the one in terms of the reaction that you flip. Because when you look at SRP reactions, they're all reduction reactions, right? So both of these reactions that were given to us from the table, they're both reduction reactions, which means in order to get to the oxidation reaction, you need to reverse one of them. And again, that is typically the anode that gets reversed because they're all written as reduction reactions. And in this particular case, just equation-wise, what we see with the gold metal is it's on the product side. So technically, we need to get that gold metal to the other side, basically. So that's how we knew we had to flip the bottom one, because it's specifically the reaction that we were looking at. And just in general, when you go to the SRP table, it is always the anode, which is the oxidation reaction, that needs to be flipped. Other questions? Yeah, so again, people sometimes, and it's a very common sort of error that people make when they're doing sort of these cell voltages and SRPs and all that, is sometimes people only hear sort of the part about, oh, the most positive one is always the cathode. And that is, again, true if you're not given any type of information. But if you are, again, given a reaction or something like this where it tells you sort of how the reaction is going, you do have to look at it and see what's being oxidized, which would be your anode, and what is being reduced, which would be your cathode. Other questions on that? All right. So why don't you try another one here? Guess I'll give you some values. I don't see them up on the screen, so we'll go with this. So I'll give you the, there you go. There's the values. So, and I told you what's being oxidized and what's being reduced here. So here's the SRP values here. So why don't you calculate the equilibrium constant here and see what you come up with. So again here, work on this one here, calculate the equilibrium constant, and we'll talk about it in a minute or so. Okay, so let us look at this. And again, the key here is we're looking for the equilibrium constant. So to sort of go back to an earlier question, this is where we would want to, again, use this equation here as it is the one that sort of involves the equilibrium constant. And again, here, you could technically use either of the bottom ones as well if you wanted to. Again, because I think it was 25 degrees Celsius as well. But like I mentioned before, sometimes it's just easier to use the top one there and just kind of plug and chug into it. So let us go back here. And okay. So again, excuse me, we could use the equation that we saw earlier, which is basically our E of our cell is equal to RT NF, the natural log of K. And in this case, we do need to figure out E of our cell and our cathode and our anode. These are our SRP values that we'd find from the table. Again, here, when we look at it, we may be tempted to make this our cathode and this our anode because the silver is more positive. But if we look at the equation and the reaction, we see that iron goes from +2 to 0. So the iron is being reduced, while the silver is actually going from 0 to +1, and it's being oxidized, the silver here. So what that actually does mean is, like we see above, our cathode in this case is actually the iron, and our anode is actually the silver. So again, very important if you're given an equation to actually look at it and see what is happening in terms of who's being oxidized and who is being reduced. And again, that is how we get to our choices here for sort of cathode and anode. Now that we have that sort of all squared away, our E of our cell, E of our cathode minus E of our anode. Again, here I'm subtracting, so I'm not going to change the signs. If you change the signs, you should again here be adding and not subtracting. So our cathode is minus 0.44 minus our 0.8 volts. And in this particular case, we will end up with 0.44 minus 0.8, going to give us minus 1.24 volts. At this point, you should know that this reaction is probably going to be non-spontaneous. Again, that E value is going to lead us to a positive delta G, which also will mean it'll be non-spontaneous. And in addition, we also can predict that our K value probably should be on the small side here, just from that sort of value that we got. All right, so we got our E of our cell. R is a constant, 8.314. Our temperature needs to be converted to Kelvin. That's a constant. We do need N. So N again in this case is going to be 2. Remember, you don't add those together, so N would not be 4 or anything like that. And I think that's pretty much everything we need. So we can go minus 1.24 volts equals 8.314 joules Kelvin mole. Temperature becoming 298 Kelvin on that. When we add 273 to our 25, our N is 2 moles, and our Faraday 96,500 joules volt mole, natural log of K in this particular case. In this case, we're going to kind of clean up everything, so we will get, let's see, 8.314 times 298 by 2 divided by 96,500. That's going to give us minus 1.24 equals 0.0128. We'll call it 37 natural log of K. We're going to divide to the other side, and that will get us minus 96.594. We're going to take the E of both sides, and that will get us a K value in this case of 1.1 times 10 to the minus 42. And I would qualify that obviously as a small value of K, which we would have expected based on just really the calculation of E of the cell in this particular case. Any questions on any part of that calculation? Again, if you chose one of the other two sort of equations, and again, depending on how you round as well, because especially when we start doing sort of these E's and stuff like that, you may get a slightly different number. Let's see here. Yeah, so that is the basic definition of anode and cathode. Anode is oxidation, and cathode is reduction. So at the anode side, that's where oxidation occurs, and at the cathode side of the galvanic cell, that is where reduction takes place. And that's always it. And that's why, again, it's important that, like in this particular example here, we were given that overall reaction. We want to look and see who's being oxidized and who's being reduced, so that we can make sort of the correct assignment of anode and cathode. Again, if you're not given the equation, that's the point where you could use the SRP value, and the one that's more positive would be your cathode. Other questions on this particular one? Probably not, if it's just a rounding thing. Like I said, definitely with this equation, or some of the other those other two where you have the 0.025 and those kind of guys, you definitely will sort of see a little bit of difference. And usually the difference is with the rounding, and it's just in the first part of the number. This number here, sort of the exponent part, if you will, is usually pretty much the same no matter which one you choose. But you will get a slightly different answer on the front part of the number, again, depending on sort of how you round. So you might not want to round super strict all the way through, maybe till the end. Because if you do, especially again when you're dealing with logs or natural logs or sort of the E's and those type of things, it can make kind of a big difference in terms of the final answer, if you kind of do a lot of really strict rounding. That I think is too far off. I would just check your calculations. Hopefully others got what I got, I hope. Yeah. All right. Let's continue on. All right, so now let's talk a little bit about the concentration and sort of the effect on the cell voltage. And this brings us an important sort of equation as well. And this is basically very similar to the thermodynamic equation that we saw in the previous chapter with our delta G. So if you remember, we have that delta G sort of equation here. And again, we have the two delta G's. And again, the difference between them is that delta G naught is sort of standard conditions. So that means typically you go to the table and kind of look up the values. Under 25 degrees Celsius, everybody's 1 molar in terms of concentrations. Everybody's 1 atmosphere if it's pressure of gases. And the delta G without the naught is, you could kind of think about it as sort of non-standard conditions. So something is not like that. So maybe the temperature is not 25 degrees. Maybe the concentrations aren't 1 molar. The pressures aren't 1 atmosphere. So there's something that's sort of not under standard conditions. So like we saw in the previous chapter, you could calculate delta G sort of under those standard conditions, which would be delta G naught. And you could do that, products minus reactants. And then that'll give you the delta G under non-standard conditions when you plug it in with the rest of it. And our Q there, again, is our reaction quotient. So that's our products over our reactants, not our equilibrium constant. And we could do kind of the same thing with our E of the cell and cell voltage. And this brings us this equation, which is an important equation. This is what is known as the nearst equation. And again, the nearst equation basically will calculate the cell voltage, and it's sort of used when you're, again, are not under sort of standard conditions. So just to look at these things in here, these are all the things that we sort of seen before. Our E naught of the cell is, again, our E cathode minus E anode. That is the guy right here, and that is just straight from the table of the SRP values. RTNF, that's all the same stuff we just used. So that R is our gas constant, which is the 8.314. The T is obviously the temperature in Kelvin. F is our Faraday's constant, our 96,500 number, and our N is our number of moles of electrons. Our Q is the same Q we've seen all semester here. It's our products over our reactants. Again, obviously you use the coefficients as those exponents, just like normal. And if something is not correct, and this is usually where you'll kind of see that difference, something about concentrations, pressures, something like that, we get then calculate this E here, and this E here is the E of the cell under sort of non-standard conditions. And just like we saw in that previous equation, if you want at 25 degrees Celsius, they do sort of reduce down to those same numbers that we saw previously. And just like the other equation, you basically can just plug it into the one in the box there, all the numbers, and it'll come out the same. This equation, the nearst equation, is really, how we get to the equilibrium constant equation that we just used. Because when we're at equilibrium, as we saw earlier, at equilibrium, E equals 0 and Q would equal K, which means if you rearrange that equation, that is how we get to our equation that we just used. So really the equation that we just used, kind of comes from the nearst equation. When you're at equilibrium conditions, E would equal 0 and Q would equal K. All right, so this is the nearst equation. You want to use it for non-standard conditions. You can figure out how the cell voltage will change if you perhaps change the concentration, if you change pressures, whatever it may be, if you're dealing with gases. And again, this is an important equation. So why don't you give that a go there? So here's some values that you need. And we want to know, will the following reaction occur spontaneously at 25 degrees Celsius if the concentration of iron 2 is 0.6 and cadmium is 0.01? So take a moment and see what you come up with. Okay, so let's take a look here and see what we got going. So we want to know, will this occur spontaneously? And we have some concentrations given to us. So the first thing that we should notice, obviously, is these concentrations are not 1 molar, which would imply that perhaps this is not under standard conditions. And again, under standard conditions, we assume that everything is 1 molar. So we probably want to use our nearst equation here. Excuse me. And our nearst equation, as we saw on the previous slide there, was, come here, E equals E naught minus RT NF natural log of Q in this case. And we do need to figure out a couple of things. So again, our E naught there is our cathode minus anode. So we want to figure that out. Although in this particular case, it did give it to you. It won't obviously always give it to you. Again, this is a situation where we do not want to go by the most positive, which would be this guy, as our cathode, because again, if we look at the actual reaction, our iron again is going from +2 to 0, which means it is being reduced, right? And by definition, that would be our cathode. While our cadmium is going from 0 to +2, it is being oxidized. And again, by definition, that means it is our anode. So to calculate E of the cell under standard conditions, again, we're going to take cathode minus anode. Again, I'm subtracting, so I'm not going to change any of the signs. So our cathode is our iron, which is minus 0.44 volts, minus our anode, which is minus 0.4 volts. And that will give us an E of the cell under sort of standard conditions here of 0.04 negative. So under standard conditions, where again everything is 1 molar, 1 atmosphere, 25 degrees, this reaction is non-spontaneous, right? It has a negative value for E. But we're not under standard conditions. Again, we have some different concentrations. So we do also need to calculate Q. Again, Q in this case would be products, which would be the cadmium, over our reactants, which would be our iron 2 in this case. Also, why you're only given 2 concentrations, because the other guys are solids. And just like normal, we don't include solids in there. And that's pretty much everything we need. We do need electrons, right? So if we look at our electrons here, our N is going to be 2 in this case. So that should be everything we need. So our E will equal our E naught, which is minus 0.04 volts, minus our R, 8.314. Our T, which is temperature, 298, divided by N, which is R2, and our F, which is our constant. And natural log of the cadmium concentration, which is 0.01, divided by our iron there, which is 0.6. Any questions on that part of the calculation? All right, so let's do some cleaning up here. We're going to take, let's see, we'll clean up the outside first. So we end up with minus 0.04 minus 0.0128. I'll take it to a few digits, times the natural log of 0.016667. All right, so we take the natural log of that there. We're going to times it by 0.012837. That is going to get us minus 0.04 minus minus 0.05256. And lastly, that should get us 0.01, I'll round to 3 volts. Any questions on any part of that calculation? Now, what we do see is under standard conditions, this cell would be non-spontaneous. It would not occur because we do have a negative voltage over here. But by playing with the concentrations, it will technically become spontaneous under these conditions. Not by a lot, 0.01 volts, basically, that's not a lot of voltage. But technically speaking, we do have positive voltage at this point. By playing with the concentrations, we obviously were able to sort of increase the voltage by like 0.05 volts or so. And we did get to basically a positive voltage. Any questions on any of that sort of calculation there? Yeah, so in this particular case, it's okay because the temperature again is 25 degrees Celsius. So just to clarify, and again, probably not a big issue in most of the problems that you would do, but those two bottom equations, just like the two equations that had the kind of the same numbers that we saw earlier as well, these are technically for a situation when you're at 25 degrees Celsius. And again, probably most of the problems will be sort of that situation. But technically, if you're not at 25 degrees Celsius, you shouldn't use those kind of reduced down versions. You should use obviously the one in the box here. But again, you can use the one in the box at 25 degrees Celsius as well, like I just did, or you can use the two bottom ones. Again, you should get pretty much the same answer. And as we talked about before, might be slightly different with depending on how you round and stuff like that, but it should be pretty darn close and stuff like that. Other questions? Okay. So I think you got another one here. Oops. Yeah. All right. So give this one a go here for the following. Balance the redox reaction and calculate E of the cell and the equilibrium constant. When it says balance, just balance out the electrons and add them together. So take a moment or two and see what you come up with. All right, so let's take a look and see what we got going on. So here we want to sort of balance. We want to figure out E of the cell and K. So a couple of things. Again, that really will bring us back to that equation that we solve for the equilibrium constant, since that's what we're looking to calculate here. And again, that was E equals our RT, our NF, natural log of K. Again, that's the one that we could get from really the nearst equation when we get to sort of equilibrium conditions. Now, we do want to figure out sort of what's our anode and our cathode. And again, if you just look at the values, we do have the 0.17, which is a larger value. And again, that may make you think that the cathode, and this would be our anode. But we do want to verify by looking at the equation here and seeing what's going on. And in this equation, we could simply look at the chromium, really. It's kind of the simplest one. We see the chromium's going from +2 to +3. So it's actually being oxidized, right? So our chromium is being oxidized, which does mean it will then be our anode. And in this particular case, if you just kind of blindly went with the more positive one, you would be okay. But again, I would highly recommend you double check the equation to see what's going on, because as we saw in several of those examples, it doesn't always sort of follow the more positive one. So technically our anode would be our bottom one, which we would want to flip. And if we flipped it, actually what I'll do is I'll just write it above. It would go like that. It would go to this plus this. We also would need the same number of electrons, so we would need to multiply it by 2. And our E value, again, if I flipped it and you want to write the correct E value, it would be positive 0.5 volts. What I'm going to do is just kind of put a line through here. And really at this point, we can add it together, these two reactions. Our electrons will cancel, and that will leave us our 2 chromiums plus our S4O62 minus goes to our 2 chromiums on the other side minus. Now, in this particular case, since I actually did flip the sign, I could find E of the cell by really just adding them here. So I'm going to add because I already changed the sign. So basically our E of the cell in this case would be 0.5 plus our 0.17, and that's going to give us 0.67 volts, which should not change that. Oh, come back. Which should tell us that this reaction is going to be spontaneous based on the positive voltage. That also, again, should tell us that our equilibrium constant should be a large value as well. Yeah, so remember that, and these are really just basic sort of redox reactions. So whenever you add the 2 half reactions, or oxidation half reaction and reduction half reaction, you always want the same number of electrons. So sometimes it does require you to multiply one of the half reactions by a number. It may also require you to multiply both half reactions by a common number. The key, though, is here when we deal with the SRP value, as we talked about, even though you had to multiply like I did there by 2, it will have no effect on the E value for that particular half reaction. So unlike a lot of things, when we multiply across, we change things like the delta H value gets multiplied, the K value gets squared or something like that. Here, though, the SRP value, the E value, will not be affected by having to multiply. So that's an important sort of distinction, but we still have to multiply by that to balance out the electrons. Other questions on that? And again, that 2 is important as well for the other thing that we need to calculate, which is in this equation. We know that the N then obviously does equal 2 in that case for our electrons. And at that point, we have everything that we need, I think, to solve for K. So that would give us 0.67 equals our 8.314. And cut out the units as I'm running out of screen here. 298, we'll assume that it is 25 degrees, even though it didn't say. Would have probably been helpful there. 2 moles and our 96,500. And that's going to give us our natural log of K. So if we sort of clean up a little bit here, everything that we got going on, we got 8.314 times 298 divided by 2 divided by 96,500. Going to give us 0. Find where I'm writing. There it is. 0.67 equals 0.012837 natural log of K. We're going to take 0.67 and divide it by that. Going to give us 52.1922 equals the natural log of K. We're going to take E of both sides there. And when we do, K will equal 4.6 times 10 to the 22, which again does make sense. That obviously is a large value of K, which we would expect obviously with a cell voltage being positive. And thus we would expect products to be formed in this particular case. Any questions on any of those parts of the calculation, why we did any of that, how to use any of these equations? And again, in terms of the nearst equation, which is the one we used previously, just to make that point, or just go back real quick. Again, people will sometimes do the plus here, the positive instead of the subtraction. So keep in mind that that's actually a subtraction on the nearst equation that we use. Any question on any of these things? So obviously you need to be able to, sort of balance these equations, figure out E of the cell, figure out delta G, figure out the equilibrium constant, use the nearst equation in non-standard conditions. Any questions on any of that? Okay. So we're just talking a little bit about batteries here. So we've got a few minutes. We can kind of get into that as well. So we're going to talk about some batteries. You're going to see some different types of batteries. And I don't know. You're not going to be responsible, for example, to give any half reactions for batteries or anything like that. So it's just a sort of a general information, I guess. So a battery really is just a galvanic cell, or really a series of galvanic cells that are basically hooked together as a source of really direct electrical current and a constant voltage. They're self-contained, so the nice thing, unlike a traditional galvanic cell, obviously you don't have beakers of sloshy solutions moving around. You don't need a salt bridge or anything like that. So they're sort of self-contained, but the basic operation is very much like a galvanic cell, and it's really basically just a redox reaction that occurs. So let's take a look at some different types of batteries. And again, you're not going to be required to know these half reactions for batteries, or any of those type of things as well. So this is a battery here. I can go with perhaps a Duracell. I won't. It's not labeled there, but it's a dry cell. And in this type of cell, we basically have a anode, which is sort of the zinc can that's in contact with a sort of an electrolyte solution in the middle. And the cathode is sort of the carbon rod, that's immersed inside the center there. And again, on batteries, just sort of like on galvanic cells, we have minus and our positive, right? And again, just like in a galvanic cell, electrons would be traveling obviously from the minus to the positive end of a battery, which is why, again, when you put a battery into a piece of equipment, you need to put it in correctly to get yourself really a positive voltage that's happening. If you put the batteries in backwards, it doesn't work, because basically your anode and cathode is sort of reversed, if you will. So we typically need to put batteries in correctly. And again, it's basically, when you look in the battery compartment, right, there's wires and stuff like that, which allows the electrons basically to travel, sort of power your device. So this type of battery You typically will give you a voltage of 1.5 volts. It also has this moist paste in the middle, something like zinc chloride and ammonium chloride. That is, those are good electrolytes, right? So sort of that paste in the middle, we sometimes call battery acid, right? And all that kind of stuff when it starts leaking all over the place. That basically is what will act sort of like the salt bridge. That helps keep everything flowing in terms of charge, like in a traditional sort of galvanic cell. We have that sort of salt bridge that connects both of the sides. On the anode side, we see our zinc going from 0 to +2, being oxidized. And on the cathode side here, we have our Mn, which starts at like +4 there and ends up at +3, so gaining electrons here in terms of reduction that's occurring. They come in different sizes, right? You have A's, double A's, triple A's, C's, D's in terms of battery. They all pretty much give you the same voltage, but again, sort of the size of the battery is able to sort of continue with this process and sort of work for a longer period of time. Another type of battery is a mercury battery. And again, you're not responsible for any of the reactions or anything like that. But again, used a lot of times in sort of medical devices as well. A little bit more expensive than sort of that dry cell that we just saw there. Also has the anode as sort of a zinc that's has some mercury in it as well. It's in contact with a strongly alkaline electrolyte. Alkaline means basic, so a strong base obviously is a strong electrolyte, which obviously means it produces a lot of ions, helps conduct electricity, keeps all the electrons really moving along. The nice thing about this is there's kind of no change in the electrolyte composition during operation, and that keeps basically this battery going for a long period of time. So it has a really long life. The sort of inner part, if you will, basically maintains itself and stays there for a long period of time. And that allows this battery basically to operate for a long period of time and have a very high sort of capacity. Again, when we look at it here, we've got our zinc going from 0 to +2. And we got our mercury here going from +2 to 0 in terms of oxidation state being reduced. And this is also a pretty good hallmark for batteries in terms of long life and sort of rechargeability. When you have a lot of solids in the overall reaction on the products and reactant side, that means it's able to basically be maintained over a long period of time. It doesn't sort of degrade a lot. And that's very big in terms of things that are sort of rechargeable and those type of things. There's also like our lead storage battery, right, which is basically our car battery. And that's basically 6 sort of identical cells together in a series. And each cell basically has a lead anode and a cathode that's made up of lead dioxide. Also, usually we'll have something like sort of battery acid, sulfuric acid type solution used as an electrolyte, obviously a strong acid, which provides a lot of obviously charge to keep everything going. Each of those cells can produce about 2 volts, which gives you 12 volts, which is enough to start your car, except on those days when you're late, right? And it doesn't want to start. It should be enough to hopefully kick it off and sort of charge it and get the car going. It's rechargeable, which means by providing sort of alternating current, it kind of keeps the battery charged, right? And that's why we have things in our cars like alternators and those type of things to sort of prevent the battery from fully discharging as we sort of drive around and stuff like that. Here's again a picture of a cross cell of basically a car battery. Again, you can see if you line up these cells in sort of a series, you could get a bigger volt. There's your anode, right, which is your negatively charged, your cathode, which is your positive terminal. Nowadays, in a lot of cars, these batteries are actually like in the trunk and the back seats. They actually are not in the actual engine compartment, although they oftentimes will have these sort of guys where you could jump your car. And then you have that big question everybody always has, right, is does the red go on the positive or the negative? Is the black on cord on the positive or negative and stuff like that? But again, you could also see that there's the acid in there as well. And you could be able to look at the reaction here and see that the lead here is going from 0 to +2 being oxidized. And on the other side, excuse me, we're going from lead 4 to lead 2. And again, it's being reduced in this particular case. Again, when you look at the overall reaction, we see a lot of solid things that are there. Again, very important for sort of rechargeability and sort of long life in terms of batteries being able to be used over a long period of time. This is a lithium battery, and lithium is a light metal. And also why they use it for, you know, like tools and electronic devices. It's a very light metal. It can be recharged a lot of times. And again, it has basically lithium as your anode, and it basically has holes in the electrolyte that allows those lithium ions basically to travel to the other side. And as you can see, the electrons will be traveling around and being used to power something like a motor and stuff like that. And a lot of those rechargeable things like your drills and your power tools, right, are all lithium batteries, a lot of them. And again, it can be charged over and over again, mainly because it's sort of a solid state. And again, like I said, that allows for less sort of degradation of the products that you need for these reactions basically to occur. And they're able to basically kind of occur over a good period of time. And lastly here, a fuel cell, which is, you know, typically not a traditional battery, but a fuel cell is basically an electrochemical process. In this case, this is a hydrogen fuel cell. It requires basically hydrogen gas and oxygen gas to be kind of floated in there together. On the anode side, our hydrogen is going from 0 to +1, so it's being oxidized, and our oxygen is going from 0 to -2 and is being reduced in this particular case. And this years ago is sort of what they wanted to sort of develop, you know, for cars and stuff like that. Obviously, sort of hydrogen powered cars, obviously didn't take off tremendously a lot because obviously hydrogen gas, for example, and that type of stuff needs to be dispensed a little bit differently. And we're more of an oil sort of economy. We have been for years, but obviously we've now moved maybe away from sort of this idea of a traditional hydrogen fuel cell. The real main attraction to that obviously is, as you can see at the end there where the arrow is, it basically produces water, so it would cut down a lot of pollutants and stuff like that. But obviously we've now gone more electric or hybrid, where we have smaller engines obviously, and sort of battery powered or just straight battery obviously as well, that we have now. So when they first tried to get, you know, off of sort of gas and that type of stuff or reduce it, this was sort of the hope, to do some type of fuel cell like this, where again, you know, it provides really less pollution and stuff like that. But again, we've sort of moved more to the hybrid model and batteries, electric type cars. All right, any questions on that? So I think we'll stop there, obviously, for today in terms of lecture. We're almost done with this chapter, actually. We just have there's a couple more things to talk about, and then we'll be done. So on Thursday, we'll finish up the rest of this chapter in terms of lecturing, and then we'll roll into the next one, which is, I think, chapter 19, transition metals and stuff like that. So we'll probably knock out most of that chapter as well, probably on Thursday as well. So we'll take a little break. So we ran a little bit long here, so maybe like 11, maybe like 11:40 or so. We'll open up the lab section. You can come through the lab, and I'll just talk a little bit about the lab. I didn't get a chance to post it there. I had to do a couple of things, so it'll be posted up shortly. The next lab, which is the one that's scheduled for today, which I think is basically redox reactions and stuff like that. And we'll talk just a little bit about sort of the parts of that. And then again, I'll be there if you have questions on that or anything else, and you can ask them. So we'll start the redox experiment today, which I think is the oxidation reduction sort of title. And probably on Thursday as well, I'll probably open up the electrochemistry one. I think they were still kind of modifying it and stuff like that. So hopefully that'll be available soon to put up. But we'll officially start the oxidation reduction reaction experiment today. And it's not up right at this moment, but right around when lab starts, it'll be up there. And then we'll just take a little couple moments at the beginning and sort of just talk about it. It should be pretty straightforward. And then again, you could go and work on it and stuff like that. Any questions on anything that's happening? I do know we have an exam schedule coming up shortly. Well, I'll have more information exactly when that will be on Thursday. We'll kind of see where we are in terms of lecture as well. Any questions on any of that? Okay, so lab will start about 11:40-ish there. Make sure you come through the lab lecture if you are going to come and listen. And again, around that time as well, this experiment will be up there. This coming experiment will be pretty much kind of like the previous one, nothing to type or anything like that. It will just be kind of fill in the paper and upload them and stuff as you do the experiment. Okay, I'll see everybody in about 20 minutes or so in the lab one.